Jnanam Paramam Dheyam. Knowledge is supreme.
So we are studying the field extensions by adjoining the roots of unity. So we have just now checked that the Galois group of the splitting field of x power n minus 1 over a field K where this n and characteristic of K are co-prime, this Galois group can be identified with a subgroup of Z mod n units in Z mod n. And we will know this order, we know phi of n. So therefore order of this group divides phi of n, but we want to find exactly what is the order of this group, and that we will do it in two steps. First, I will assume the characteristic of K is 0. That means I will assume that K is Q, and the next I will assume characteristic of K is positive. These are the two things I will assume. So as you see, minimum I want to exactly find the order of this group. So to find order of this group, this is what our aim is, to find this order. But because this extension is Galois, this order is nothing but, and this extension is simple, which is generated over K by a primitive root of unity, then this order is exactly equal to the degree of the minimal polynomial of zeta over K, and we want to find this degree. Moreover, actually we want to find what is the minimal polynomial in case of Q and in case of characteristic positive. This is what our aim is. Before I go on, this extension, remember this extension, this is called cyclotomic field extension. I will want to justify this name cyclotomic. So that is done as follows. Let us, for the understanding, let us take K equal to Q. Then what did we do? We have n, any natural number non-zero, and no condition because the characteristic is 0. And what did we do? We are looking at the roots of these polynomials. This is the polynomial, this is the polynomial over Q, and we are looking at the roots, zeros, all zeros of this polynomial. So this one is over C. These are all zeros, and we know this, they are all simple zeros because this polynomial has no repeated root, again because the derivative and this polynomial don't have any common zero. So these are all distinct, and therefore cardinality of the zero set is nothing but the degree of the polynomial, which is n. They are precisely n zeros. And what is their location? So this one is all z in complex numbers such that z power n is equal to 1. So therefore you have this circle, unit circle, all of them lie in this. Z power n is 1, therefore mod of z power n is also equal to 1, therefore mod z will be 1, so it will be on this circle. So for example, if I want to locate n equal to 2 So n equal to, let us say 2. There are exactly 2 zeros, and what is the location? So 1 0 is 1, this is 1. Remember, this is 1. Actually, strictly speaking, we should write 0 1, but this is 1. Strictly speaking, we should write 1 0, not 0. 1 0, and this is minus 1. So these are the 2 zeros. If so, this is n equal to 2 case. If I want n equal to 3 case, then there is only 1 0 is a real 0, that is somewhere here, and then another here and another here. So this circle gets divided into 3 equal parts, and then these are the things. 4, for 4 it is 1 minus 1 obviously, and this is, now I should write it I, because that is the identification of these points on the real plane with the complex number. This is I is actually 0 1, and then the other one is this is minus I, and so on. So all these zeros are lying over the boundary of this unit circle, and they are equidistant. So in general, the zeros are precisely e power 2 pi k I by n, where this n, k is from whatever g1 to n minus 1. Actually, yes. N actually. Okay. So they are the zeros. So the cyclo word comes from the circle. They are all on the circle. Main problem is to find. So our goal is to find minimal polynomial of zeta over q. I am taking the case k equal to q. So this is the minimal polynomial of zeta over q, where zeta is the primitive, a primitive nth root of unity. This is what we want to find, and this is a polynomial in Qx, monic, and zeta is a 0 of this polynomial. That is what information we know. Moreover, more information we have is this mu zeta q, this divides x power n minus 1 in Qx. This is another information. So therefore, we want to find the prime decomposition of x power n minus q. This is actually also a polynomial in Zx. And this is a irreducible polynomial over q, therefore it is irreducible over z also, because it is a monic polynomial. So monic polynomials are whether irreducible over q and irreducible over z, they are same. That was also Gauss's theorem. So therefore, we want to find a prime decomposition of this polynomial, and the one which is only one of them, only one prime divisor of this. First of all the prime divisors will have multiplicity 1 only, because this polynomial has distinct roots. So no prime divisor will also repeat. So the prime decomposition of this polynomial we are interested in, x power n minus 1 in Zx, and one of the prime factor must be this. All right. So how do we find that? All right. So what we do is the following. So we have this polynomial x power n minus 1, and we know all the zeros of this polynomial are precisely the roots of unity, nth roots of unity, and all of them lie in our field extension q power round bracket n over q. This is the field extension we are studying, and all the zeros of this polynomial are in this field. Okay, so this one is therefore a product. Product is running over zeta. Zeta is an element in mu n qn. This is by definition. This is all those elements in qn where that power n is 1, but they are all of them are here. That is how we have noted that this is a splitting field of this polynomial. So all the roots lie here, and all the roots are elements of this. So this x minus zeta. This decomposition is where? This decomposition is in q n x. But that is not what we want. We want actually in qx or in zx. Alright, so this I am going to rearrange this product. So this product is same thing as this product is running over elements in some group, cyclic group. So therefore, and the order of that group is n. This is the group. Order of this group is n. So therefore, every element of this group will have order. The order will be positive order, and orders are precisely the divisors of n. So this product, first of all, I want to divide into the according to the order. So this is product d divides n, and then product where orders of these elements equal to d, and take their corresponding linear factors. So I have just rearranged d divides n and order of this element d. So that exhausts all elements of this group, because this is a group, and therefore elements have order d, which are divisors of n, and then this. Now this inside thing I am going to define that as phi dx. So therefore in this is the product d divides n phi dx. So this polynomial is written as a product of these elements, where phi d x is by definition product. Product is running over order d elements, and zeta is an element in mu n q n x minus zeta. This is what the polynomial is, and therefore we know what is the degree. Degree of phi d, this is clearly the number of elements of order d in this cyclic group of order n. So that is phi d. This is the number of elements of order d in the cyclic group mu n q n, and therefore it is the Euler's phi function phi d. All right. Now I want to check that the coefficients, I want to know where a priori this is a polynomial, where this is a priori this is a polynomial over this field, but I want to check that this polynomial actually has integer coefficients. So the polynomial phi d x has coefficients in the prime field of K. Now I don't even have to assume Q. This will work for arbitrary field till here. So prime field of Q, and where K is Q, what is that prime field? That is precisely Q, which is Q or Z mod P if the characteristic of K was P, positive. Anyway, we do it for first the characteristic 0 case, which is P. So I know how am I going to prove this? So the coefficient I want to prove that they are in Q. Actually, I want to prove that the coefficients are in Z actually. In case of Q, coefficient, so let me write. So when K equal to Q, we will prove that phi d x actually the polynomial over Z for every d divisor of n. This is what I want to prove. And this I am going to prove it by induction on D. The proof by induction on D. So let us see what is when D equal to 1. What is phi 1? Phi 1. Phi 1 is the product. Product is running over all elements of order 1, but there is exactly one element of order 1 in any group, namely the identity element. So that will be 1. So that is this. Phi of 1 is x minus 1, because 1 is the only element in that group of order 1. Yes, 1. Mu n q n. This group has only one, so identity element is 1. So, and this is only one element of order 1. So it is phi 1 is 1. So D equal to 2. D equal to 2. How many elements are there of order 2? There exactly one element of order 2, namely minus 1. Because in any cyclic group, order of elements, the number of elements of order D are precisely phi D, and phi of 2 is 1. Therefore, there is only one element of order 2, which is minus 1. Therefore, phi 2 is what? Phi 2 is x plus 2, x plus 1, x minus minus 1, that is plus 1. So phi 2 is this. So induction starts. Now for any, I assume that up to, I only have to prove that the last one, because if D were strictly smaller than n, then we know we have proved by induction that all these phi 1 etc., all this phi, the last one, I don't know what it is, the divisors, this one where this D is strictly smaller than n, all these, and there is nobody, the next one is only phi n, all these elements have coefficients in Z, and now I want to prove that this one has coefficient in Z. But look, we know that when you divide a polynomial over integers by a monic polynomial, the divisor, quotient and the remainder, they are unique elements. In the division algorithm, quotient and the remainders are uniquely determined. So therefore, if I want to divide this polynomial x power n minus 1 by the product phi d, where d is strictly smaller than n, and all of them, nobody after that, and d is strictly smaller than n, d divides n and d not equal to n. These are already, we have checked that all these polynomials are by induction are in Zx. So the product is in Zx. This is monic polynomial. So when I divide this polynomial by this product, what do I get? I get this x power n minus 1 divided by this product, that is d smaller than n, d not equal to n and d divides n. This is nothing but phi d, phi n. Because we know x power n minus 1 is a product of all phi d's and only one is left. So therefore this, when I perform the division algorithm by this polynomial, divide this polynomial by this one, then I get a quotient and I get a remainder. There is no remainder because this divide this and the quotient is precisely this, and this is unique and this happens in Z. So therefore we have no choice, this has to be in Zx. So therefore we know that all these polynomials phi n are have integer coefficient. So this polynomial phi n, this phi n is called nth cyclotomic polynomial. Nth cyclotomic polynomial. Okay. Now, what was our problem? Our problem was to find if I have zeta, which is not arbitrary element but the primitive element. If this zeta is a primitive element, that means a generator of mu n. So the order of zeta equal to n. Therefore that x minus zeta comes in it's a factor of this phi n. So therefore I definitely know. So this shows that phi n of zeta, this is 0, not only for one primitive, this is true for all primitive nth roots of unity, because they are precisely the generators of this group mu n q n. So therefore we must prove that if k equal to q, we must prove that mu minimal polynomial of zeta over q is nothing but phi n. If we prove this, then we will know. What will you know? So suppose we prove this, then we will know that the order of the Galois group which is equal to the degree of mu zeta q, which is degree of the polynomial phi n, but phi n I know degree, this degree is phi of n, because phi n is precisely product of all linear factors which are number of elements of order n in this group, and they are precisely phi n. So this is precisely the degree phi n. On the other hand, this was a divisor of this group, was a subgroup of the unit group of Z mod n cross, and therefore this order was a divisor of this, but this the group of this order is also equal actually. So therefore we get that the Galois group is, so from this we already infer that the Galois group of Qn over Q is actually Z mod n cross, because it's a subgroup and the orders are same, therefore it has to be equal. This is isomorphic, and this is a canonical isomorphism. This isomorphism is any automorphism of Qn over Q. This is mapped to the restriction of that automorphism, and that is thought as an automorphism of this group, this cyclic group mu n Qn, which is a cyclic group of order n, and therefore automorphism group has order phi n, and which is actually this group. So that gives a complete description of the Galois group of Qn over Q, provided we prove that this polynomial is the minimal polynomial of this one. So that needs a proof, and that is the only non-trivial proof so far. So I will state it as a theorem. So theorem is what now? N is any non-zero natural number, then the nth cyclotomic polynomial phi n, which is a polynomial in Qx. This is defined by the product x minus zeta, where order of zeta equal to n and zeta power n equal to 1. So it's a nth root of primitive nth roots of unity, all the product. This is irreducible over Q. Actually, I should write better. I should write is a prime polynomial. It's a monic polynomial, and it is prime means it's a monic irreducible polynomial. And this is, we will prove this next time. We will need a little time to prove this, and I will postpone the proof to the next one. So to summarize, what did we do today? What we did was the main two examples. One is the finite field, finite extension of a finite field. This is Galois group is actually, we proved it's a Galois extension with a Galois group cyclic generated by the Frobenius automorphism. And in the second case, we proved that if you take the roots of unity, the splitting field of the polynomial x power n minus 1 over q, this splitting field is a Galois extension of q of degree phi n, and the Galois group is abelian. In fact, the Galois group is the unit group of the ring Z mod n. And then next time we will prove this theorem, irreducibility of the cyclotomic polynomial over Q, and we will further now analyze what happens if I take characteristic P fields, in particular finite fields. What happened to the Galois group of the splitting field of the polynomial x power n minus 1 over a finite field of characteristic P. Thank you.